This video is on the electrochemical series. And our aims for this video are to use the electrochemical series to calculate the EMF of a cell and use the electrochemical series to predict the direction of redox reactions. So if you don't understand what this table really shows, then you can watch one of the other videos on electropotentials. But basically what I've got here are a number of electropotentials for different cell reactions. And to calculate the EMF of a cell, we've got to basically use these electropotentials to do that. So if I'm just going to take two random choices, so I'll take the chlorine electrode and I'll take the ozone electrode. If I was to connect those two electrodes, the EMF of the cell would be the difference between the two electropotentials. So the EMF of this cell would be 2.08 take away 1.36, which equals 0.72. Now, depending on which way round these two half cells were connected, you could also say that EMF could also equal minus 0.72. And which one you choose will depend on if there's a cell representation given, which again is covered in one of the other videos. And basically, if you have a cell representation, the right-hand electrode in that cell representation determines whether it's a positive EMF or a negative EMF. So if we say that the ozone electrode was the right-hand electrode, then because it's the more positive electrode at the two, so it's plus 2.08 compared to plus 1.36, then the EMF would also be positive. If it was the other way around, the chlorine electrode was on the right-hand side, then because the chlorine electrode is more negative than the ozone electrode, then the EMF would be negative. So it's all based on the cell representation and what the right-hand electrode is. So we can also use these electropotentials to work out the direction of redox reactions. If we take the same two reactions, the chlorine electrode and the ozone electrode, if we were to connect those two half cells together, then we can use the electropotentials to work out what the reaction would be. So we've got to think about which way the electrons would flow. So the more negative electrode is going to have electrons flowing from that to the more positive electrode, because the electrons are going to be attracted to the more positive electrode. So here, electrons are going to flow from the chlorine electrode to the ozone electrode, which means electrons are going to be lost from the chlorine electrode, and electrons are going to be gained by the ozone electrode. Now, if we look at the two half equations, you can see that all the half equations are written as if the thing is being reduced. So the Fe3 plus is being reduced, the chlorine's being reduced, and so on, because the electrons are being added to the reactant side. So if electrons are being lost, that means that the half equation where the electrons are being lost would need to be switched around. So we can write our two half equations out as 2Cl minus goes to make Cl2 plus 2 electrons, and O3 plus 2H plus 2 electrons goes to make O2 plus H2O. So if these two cells were connected together, the overall equation would be, if it was discharging, 2Cl minus plus O3 plus 2H plus goes to make Cl2 plus O2 plus H2O. So if we were to connect these two cells together, then when electricity is flowing and we're getting a voltage, that's the reaction that would be happening. If we were recharging the cell, if it was a rechargeable cell, then the opposite reaction would happen when the electrons are forced back the other way. So the best thing to do to show you this in practice is to show you some past exam questions. So here it says some electropotentials are shown in the table below. These values are not listed in numerical order. So in order to confuse you slightly more, they tend to put the half equations not in numerical order, which means you have to just have a look down the table to find the lowest and highest numbers and things like that, which just makes it a little bit more awkward in the exam. Just make sure you don't fall into a trap there. So it says identify the most powerful reducing agent from all the species in the table. So the most powerful reducing agent is going to be the one that is oxidized most readily and therefore loses electrons most readily. So the one that's going to lose electrons the best, if you like, is going to be the most negative electrode, which, if you look down the list, is this one here, plus 0.68. That's the most negative out the lot. Now, if that is a reducing agent, if you're going to reduce something else, that means it's going to have to be losing electrons, which means that the thing that's actually losing electrons in this half equation is the H2O2. And so H2O2 is the most powerful reducing agent in that table. And then it says, use data from the table to explain why chlorine should undergo a redox reaction with water. Write an equation for this reaction. So, whenever you're asked to explain why something will happen based on electropotentials, all you're going to do is compare the two electropotentials to each other. So you're saying why chlorine should undergo a redox reaction with water. So, first off, there are two equations where water is present, and there are two equations where chlorine is present. So you've got to make sure you choose the correct two half equations to show this happening. So the two that you need to choose are where the chlorine is being turned into something else. So we can either have the chlorine here being reduced or the chlorine here being oxidized. So here we've got the chlorine being reduced, and for it to be reduced, it needs to be able to gain electrons from something. And the water electrode where it's going to gain electrons will be this bottom one, because the electropotential here is more negative than the electropotential here. So what will happen is the electrons will flow from this electrode to the top one. Therefore, the water will lose electrons turning into oxygen 4H+, and the chlorine will gain electrons turning to Cl-. To explain why that will happen, all you have to say is that the electropotential of the Cl2 Cl- electrode is greater than the electropotential of the water oxygen electrode. You need to make sure you state what's on both sides of the equation, not just on one of them, because there is more than one electrode you could choose. If it was worth more than one mark, that bit, you'd then say, therefore, chlorine is reduced by the water. And then the equation will be, the water equation needs to swap round. So you've got 2H2O turning into O2 plus 4H plus 4 electrons. You need to multiply up the top one by 2 so the electrons cancel. And so you're going to get 2Cl2 plus 2H2O goes to make 4Cl- plus O2 plus 4H+. Slightly easier question here. So it says the half equations for two electrodes used to make an electrochemical cell are shown below. There they are. Write an overall equation for the cell reaction and identify the oxidizing and reducing agents. The overall equation is going to be these two things combined together, but we need to choose which one we're going to swap around first. So the electrons are going to flow from the more negative one to the more positive one. So the bottom one to the top one, and therefore the bottom one is losing electrons, therefore being oxidized, and so that's the one that's going to be swapped round. We can also multiply up the electrons as we do this, so the electrons are cancelled. So they have to multiply up the whole equation by 3, so that both equations have 6 electrons. So this bottom one's getting switched around, so what we're actually going to get is SO3 2- plus H2O, and we're multiplying all up by 3, aren't we? So there we are. Goes to make 3SO4 2- plus 6H plus 6 electrons. And so the overall equation is those two added together, not this one. Just swap that around. So the overall equation is going to be 3SO3 2- plus 3H2O plus ClO3- plus 6H plus goes to make Cl minus plus 3SO4 2 minus, plus 6H plus 3H2O. Now it's important you realise that it's not just electrons that might cancel, it could be other things as well. So here you've got H plus cancelling and the water cancelling. It's really, really important to get the marks in, that you cross those out or just don't write them at all in the first place. The oxidising agent here is the thing that is being reduced itself. The thing that's being reduced is a thing that's having electrons added to it. So that's that top equation here. So that's a ClO3 minus. And similarly, the reducing agent, the thing that's being oxidised itself, so that's the thing losing electrons, that's your SO3 2 minus. And finally, it says some electrode half equations with their standard electrode potential shown in the table below. There they are. So suggest what reactions occur, if any, when hydrogen gas is bubbled into a solution containing a mixture of iron 2 and iron 3 ions. Explain your answer. So the two electrodes we're looking at here are iron 2 and iron 3 here, and hydrogen here. So electrons are going to flow from the hydrogen electrode to the iron 3 plus iron 2 plus electrode. So the hydrogen is going to lose electrons and form H plus. So one reaction that will occur is that H plus will react with Fe3 plus to make Fe2 plus and H plus. And to do that we need to multiply up this top equation by 2 and then add them together. So we'll get H2 plus 2Fe3 plus goes to make 2Fe2 plus 2H plus. And the explanation here, as I say, whenever you have to explain yourself in these situations, you just compare the electropotentials. So you'll say the electropotential of the Fe3 plus Fe2 plus is greater than the electropotential of the H2 H plus electrode. Make sure you write everything in there, and therefore H2 is oxidized by the Fe3 plus. What could happen then is, because Fe2 plus is made, you can see that Fe2 plus will gain another 2 electrons to form Fe solid, but that won't happen, because if you were to connect the hydrogen and this electrode together, actually it would be the iron solid that would react with the H plus to form hydrogen and Fe2 plus, because electrons would flow this time from the iron electrode to the hydrogen electrode. Now, because there's no iron anywhere, that reaction will not happen, and so that's where it will stop.